All right, well, thank you very much. Thank you for the opportunity to give this talk and kick this meeting off. And thank you very much for putting together this meeting. I think this is a particularly compelling topic and a particularly good time for it. So thank you to the conference organizers for putting this together and giving us a chance to have some scientific interaction in these interesting times. So I'm charged with talking about dynamical interactions in young star clusters, and as any time-limited review constructed and presented by a human being tends to be, this will be a biased and incomplete overview of some of the relevant and interesting aspects of dynamical interactions, particularly as it pertains to planet formation happening in young star clusters. So to think about a few reasons and ways in which this might be affecting the outcome of planet formation, I would look to perhaps a pretty well-populated literature of people looking at dynamic interactions in star clusters to figure out how this might affect planetary systems in general. And there are many reasons for doing this, not the least of which is that observations suggest that the vast majority of stars form in clusters. And in this case, I'm using clusters in the statistical sense that stars tend to form near other stars, and not necessarily that these are long-lived gravitationally bound systems, although people have also considered the likelihood and survival of planetary systems in bound systems like globular clusters. And so the dynamical interactions that you might get in these kinds of star clusters will quite likely affect a lot of different aspects of your planet system, including the architecture of the planetary system, particularly when you have multiple planets that will be affected by interactions with other stars and with each other in these perturbed systems, how this might eject planets from systems and lead to free-floating planets, either within the context of the star cluster or outside of the star cluster. And then more recently, I think people have been looking about how can we look at the structure of the observed planetary systems, which tend to be seen around relatively older stars, gigayears and older, and connect them to how we think their formation environment led to that particular planetary type system. And so part of that is because a lot of the known planetary systems are around relatively older stars. There have been some efforts to be looking for planets in young open clusters. A couple of examples shown here on this plot from Fujinori, where those young clusters with detected planetary systems are sort of shown on the right-hand side here in the red diamonds. So young in this case is still several hundred million years old, not so young to somebody like me who's been thinking about star formation closer to the million-year age. But nevertheless, that leaves us with a bit of a gap between where the star and planet formation is happening and where we're able to observe the systems. So if we think about sort of the dynamical evolution of these star-forming clusters as a whole, that sort of helps get us through the through line from the formation of planets to the planetary systems that we're observing now. And so for the individual star and planet forming systems, there are a couple of different ways that dynamical interactions can be affecting the planet forming system. For example, flybys, which I think we'll be discussing quite a bit more in the discussion section this afternoon, where you either have a star come by and perturb the disk, or you have another disk-bearing star come by, and you're either pumping up things in the outer disk and changing the structure and scale heights, or in the case of this animated GIF running on the right here, I believe this particular simulation was showing how you actually end up mixing materials from the two interacting disks. And they were putting this forth as a model to explain the origin of Sedna in the solar system. Another sort of direct interaction that you might get between, or dynamical interaction you would get would be between binary stars. For example, looking at an example here from Giovanni, where we have this nice spiral structure observed in a circumstellar disk that has a nearby companion star that might be exciting some of those features in the disk. I'm not going to talk too much about binary interactions in particular because we have many nice posters in the dynamical interactions session, and I encourage you to go take a look at those on Teams if you haven't had a chance to already. So looking at how that sort of dynamical behavior between the two stars affects their gas and dust radii, creates these sort of structures in the disks, and affects the kinematics of the binaries themselves. And then finally, I think these sort of dynamical interactions within the cluster region lead to something that I'm calling it an indirect effect. And trying to think of the best way to describe what this is, I ended up at the myth of Icarus, where we know that Icarus made the mistake of flying too close to the sun. But it maybe starts a little bit earlier because Icarus and his father were imprisoned, and Icarus's father, Daedalus, built wings out of wax and feathers to allow them to fly away and escape from prison. But of course, the caution was that you don't want to fly too high, too close to the sun and melt the wax in your wings, and you don't want to fly too low or too close to the sea and get them wet and have lose your buoyancy, basically. But of course, we all know that Icarus flew too close to the sun and ended up falling into the sea and drowning as a result. But I think the other important part of this myth, sort of as an analogy for what we're talking about today, is the fact that his father Daedalus also had these similar wings. As this painting from Rubens, I think, nicely shows, is that by not flying too close to the sun, those wings survived the escape. And I think the analogy here then is for protoplanetary disks that are moving through a high mass cluster near high mass stars. It's only a problem if you're too close to those ionizing sources that those effects are particularly devastating. At a safe distance, it might not be quite as destructive. So with that in mind, looking to a plot this time from Andrew Winter, kind of looking at these two effects in a star forming cluster, and in particular, how the density will affect the impacts of these sort of tidal interactions and these external photoevaporations. So we're just looking at the flux on the y-axis and the density in the region on the x-axis, and then looking at a few regions of this particular plot. Above a certain density, you'll start to see significant tidal interactions that will affect a disk of 100 AU within 3 million years. And then above, excuse me, going the wrong way. Above a certain flux, again, the same thing, you'll have significant impact and destruction on the disk of a certain size within a few million years. And just to put a couple of example regions from that paper up here to guide the eye, we have the ONC, Trempler 14 in the Carina Nebula, and the Cygnus OB2 star forming region. So this is showing sort of a snapshot in time what sort of tidal effects stars in different density regimes in these clusters might be feeling, and what sort of external photoevaporation they might be experiencing given their perceived radiation. And then if we think about this in terms of an evolving star cluster, the added part of this is that dynamical evolution means that the density of the region is likely to be evolving with time. So for example, if we think about a model of cluster formation where you started with a bunch of dense gas that rapidly forms stars, and then you expel that gas, you expect this cluster to be expanding with time, and so therefore evolving towards lower densities. In contrast, if we're thinking about a model where clusters are built up over time through, say, cold collapse and mergers of substructures, you might actually be looking at an instance where the density of the cluster is going to be increasing with time. So any given cluster is likely to be moving within this diagram throughout its evolution. And I would argue we want to look at this full parameter space to understand also the diversity of sort of star forming environments and therefore planet forming environments that we would be considering. For example, there's some really nice work recently from Nick Wright looking at the Cygnus OB2 region, arguing based on its spatial structure and its kinematics that it has always been a low density association. So this sort of contradicts a picture where this would have had to start in as a small, compact, high-density region that has been expanding due to gas expulsion. There are not kinematic signatures of that kind of expansion, suggesting that the density in this region has always been relatively low. On the other side, and sort of towards the other extreme of this plot, looking at much higher density regions where the tidal effects are important and the photoevaporation effects are important, much more intense feedback overall. It's actually going to be more similar to the kind of star forming conditions that you had near the peak of cosmic star formation around a Z of 2. So it's a little bit strange to be talking about star formation at higher redshifts in a meeting where we're looking at the impacts on planet formation. But I would argue we should be thinking about how star forming conditions have changed over time, particularly given that we're finding planets around stars that are a few gigayears old. The solar system's a few gigayears old. And in fact, we've gotten a fair bit of information about the composition of extrasolar planets where planetesimals have crashed into white dwarfs and allowed us to get features of them. So if we're probing the stellar graveyard for information about planet formation, I think it behooves us to think about what kind of star forming conditions and therefore planet forming conditions were relevant at that time. So with that said, then the underlying thing here is the fact that stars move. And this is a point that I've heard Matthew Bate make at a variety of different star forming meetings. So to use Matthew's numbers, just to say that a star moving at about 1 kilometer a second will move 1 parsec in 1 million years. And so the dynamical evolution of the region is going to determine how that star is moving, what kind of environments that star is sampling, and what that's going to mean for its planet forming disk. So we're living in the era now where the Gaia mission has provided a great deal of kinematic information on stars and star clusters locally, allowing us to sort of probe the kinematic evolution of star clusters. So for example, Michael Kuhn has gone and looked at a variety of particularly high mass star forming clusters and looked at their kinematics to argue that many of these are showing signatures for expansion. So looking at this plot here, anything with a median outflow velocity greater than 0 is interpreted to be expanding. So this is several different clusters looked at with Gaia data. Just to zoom in on a couple of examples, this red point here is the ONC. And to zoom in on that data, you can see these are the proper motion vectors of many stars in the ONC. So higher confidence proper motions are shown with these black points, and lower confidence proper motions are shown with these gray points. So with GR2, the brighter your star, the better your proper motion accuracy. We hope that this will be continuing to improve as we get subsequent Gaia data releases coming in the future. And again, arguing based on the kinematics here that the ONC is showing signatures for expansion. Also arguing this blue point here, NGC 6530, or the Lagoon Nebula, shows signature of expansion. Nick Wright also argued that the Lagoon Nebula appears to be expanding and expanding asymmetrically based on the proper motion seen with the Gaia data release 2 data. So I think we've got multiple pieces of information when we start measuring the kinematics in star clusters. So we have these proper motion vectors here that are suggestive of stellar expansions in these two and many other stellar clusters, but there's actually more kinematic information when you start looking at the cluster as a whole. So for example, Nick Wright and Richard Parker had looked at in the Lagoon Nebula, and particularly looking at the differences in the velocity dispersion for stars of different masses, to argue that there's some kinematic evidence for cool collapse in this particular cluster. So a signature of its past state with stars falling in, and this being a cluster that was built up over time through the merger of substructure. Similarly, I think there's been a bit of a debate about what's going on kinematically with the ONC. So the Gaia proper motions and the interpretation there is that it's consistent with an expanding cluster. Velocity study of particularly relaxed cluster and kinematics are more consistent with cold collapse, suggesting that we're also seeing evidence of infall. So a bit of debate and a bit of interpretation into the kinematics that you're measuring. I think in both cases here, it's pointing to a little bit of kinematic forensics, trying to interpret the past state of what's going on in these particular star clusters. And so to look back, we would want to look both at earlier clusters and perhaps look at the initial conditions for how stars are forming and what that means in terms of the starting kinematics for the system. So stars form in molecular gas, and I guess that seems like a little bit of an obvious statement, but I think worth reminding us also that the gas ends up being important kinematically, especially if star formation's inefficient. That's quite a bit of mass that's not necessarily going into stars. My computer's warning me about poor network quality. Will you give me a shout if you can't hear me at any point?
It's still okay.
Excellent. All right, thank you. Hopefully that hangs in there. So stars form in molecular gas, and I guess we think about this as forming in molecular clouds, but in fact we have decades of evidence that it's not necessarily sort of a spherical cloud, but in fact that the molecular gas that stars form out of is filamentary in structure. So showing here a suite of images of sort of a variety of star forming regions. All of these predate the Herschel satellite, which I think gave us the kind of evidence that meant we could no longer ignore sort of the filamentary structure of the gas that stars form out of. And we've had some really nice observations of the kinematics of this gas in the last decade or so, showing us that these filaments are dynamic structures, that the filaments themselves are accreting gas, growing up over time, the stars are forming in these dynamic filaments, and the filaments themselves may in fact be dynamic such that they're feeding towards sort of these hubs in the filamentary structure with these spokes of gas feeding in. And so we know that the stars are forming out of the dense gas. When you look at young stars, so say like a class 1 type star that's shown on the right side of the plot here with the red points over contours of the gas, you see the stars are highly correlated with where the gas is, but as the stars age, they decouple from the gas. And we can see that spatially on the left side of the plot, looking at the class 2 sources that are more spread out than the class 1 sources. And we can see that in the kinematics. So here we're looking at an image of NGC 1333. If we look at the kinematics of NGC 1333, in this case, looking at young and old stars now being blue dots for dense cores and red dots for stars, with the green scale in the background being the gas, looking at the spatial distribution on the left, and then looking at a position velocity diagram on the right. I think the thing to notice is the stars, so those are the red points, sample a broader range of velocities than the dense cores, which are the blue points, which stick much closer to the gas velocities. So if we try to think about how some of these pieces come together, we can look to Orion as sort of a case study here. So using some of those high quality gas observations that have come out in the last decade or so, we can look at observations from Alvaro Hikar looking the Orion filament, the ONC, and most of the Orion star forming complex, if you will. They find evidence that there's gravitational collapse within the integral shaped filament towards the OMC1, so gas feeding in towards the ONC. Again, there have been kinematic arguments that the motion of the stars is consistent with cold collapse, as modeled by Alexandra Kuznetsova in this particular GIF that we're watching here on the right of an ONC-like cluster where you see stars forming in the filamentary gas and then falling inwards towards the ONC. And then we have more recent observations looking at the populations of the stars in the ONC themselves, and finding that there's evidence for actually 3 separate pre-main sequences that suggest that there are 3 separate populations of stars with slightly different ages. So we're looking at the spatial distribution of that on the left, going from oldest on the left to youngest on the right. And you'll note that the oldest population is most spatially distributed and moving towards a more centrally concentrated and youngest population. This is something Andrew Winters pointed to as perhaps a solution to the purplid lifetime problem in the ONC. So if we think about, again, the sort of structure that we have in a star forming region that's going to be setting those initial kinematics, it's a little bit messy in terms of there's filamentary gas. It may be moving towards sort of a more centrally concentrated cluster in the hub between the spokes of the filamentary gas. And one of the things that I like about this particular picture from Matson and Jumper is that it shows the ways in which not only the gas coming in, the stars coming in might not be spherical, but also the fact that this is going to affect how the feedback is escaping the cluster. So rather than thinking of like a bubble popping, that we have gas trying to escape through low density channels wherever it can punch out of the cloud. So as the gas escapes from the cluster, this will affect the dynamics of its of the stars moving as the cluster loses its gas. How the gas moves out of the cluster may also be very important for things about how the disks ultimately get enriched, thinking about a certain class of enrichment models that require that the gas remain confined in order to sort of trap enriched material in there and force hot gas to mix with cold gas, and looking at other models that allow the gas to move onto larger scales and mix into other star forming regions. Again, something for later in the week. So one last thing to say about the role of gas in terms of the dynamics of the region. I think often think about it, about what happens when we remove the gas from the cluster, changing the potential of the cluster. Just wanted to highlight some recent work from Manuel Zamora Aviles, who was arguing that the gas itself can still be a gravitational player, so to speak, once it's cleared from the cluster. If you have sufficient mass, they were arguing in this case, you basically get gravitational feedback, that there's enough mass in the gas outside of this lambda Ori-like cluster to actually be pulling the stars out of the cluster and aiding the dispersal of the cluster. So we've looked at some of the ways that these regions evolve and how the gas with the regions evolve to think a little bit about how that gets us back to planet formation in particular. Could start thinking about what we're looking at when we're looking at a population of planet-forming disks within a star-forming region. So we're typically assuming that we have a single-age population, and so that we can look at clusters of different ages to try and understand how long disks live in general. So we have the classic plot from Carl Heisch here on the left, showing that the fraction of disks as measured from the near-infrared excess decreases with time. I've put on the right here an updated version of this plot from Tomasz Prybisz, again using the near-infrared excess as a tracer of the disk fraction, but now with a few high-mass star-forming regions, high-mass clusters added to the plot. And I've just highlighted two clusters of relatively similar age on this plot, the ONC with of order 1 high-mass star and Trumpler 14 of order tens of high-mass stars that are both about the similar age, just to highlight the argument that differences in the clusters themselves can also affect the lifetime of the planet-forming disks. So highlighting, as the Prybisz paper did here, that the differences in the region, if you have more intense feedback in a Trumpler 14-like region, your disks might live for less time. There's some evidence for this in simulations as well. So looking here at simulation from Rana Nicholson, looking at the observed lifetime of protoplanetary disks shown as the symbols on this plot, and then just comparing how that changes in simulations if you have one high mass star shown in the green line here at the top versus two high mass stars, the orange line on the bottom. And indeed, increasing the number of high mass stars does shorten the disk lifetime. I think the other significant thing to look at, though, from this paper in particular was examining how the dynamical evolution of the cluster is going to be affecting the disk lifetime. So we're just looking here at two examples of clusters of different densities, lower density here on the left and higher density on the right, and looking at clusters with a variety of different structures, from more fractal, more substructured at the top down to smoother plumber sphere profiles at the bottom. And so in the lower density cluster, you'll notice that actually more substructured clusters shown here at the green actually have shorter disk lifetimes, whereas more evolved, smoother structures with the plumer sphere profile have slightly longer disk lifetimes. And this comes down to the amount of time that the low mass stars spend subject to the most intense radiation from the high mass stars. But you see in the higher density region that the disk lifetimes are lower overall, and there's much less difference between the different types of structures here. So as an observer, I'm interested to go test about how this kind of dynamical evolution in the region is then directly affecting the disks and the disk lifetime. And the question then becomes, how are we going to go out and look for this? So we have the beautiful observational example of the proplyds in Orion, shown here with the famous HST image, showing that we have a handful of these clearly irradiated protoplanetary disks kind of surrounding the high mass stars in the center of the ONC. But if we're looking in other regions, we need to try and figure out how and where we're going to find these. So just to look as an example at Cygnus OB2, we've got the broad landscape of the star-forming region shown on the right. The red points are the high mass stars, and the white boxes highlight the candidate proplyds that are highlighted on the left. So this is an H-alpha imaging survey trying to look for that kind of teardrop morphology that you see in the proplyds. And one thing you'll notice if you look at the distribution of these proplyds and the proplyd candidates in Cygnus OB2 is that they're all relatively offset from where the high mass stars are. And if we're trying to look sort of closer in or closer, different disk tracers, something like, again, the near infrared excess, if we're just looking spatially, so at stars with the disk shown here on the left and stars without the disk shown here on the right, I, at least by eye, cannot necessarily tell where the disks are versus where the disks are not being spatially different. But the argument in this paper is that if you break it down by the amount of FUV incident on the stars, then it does become apparent that you have a different number of disk-bearing stars as a function of the FUV radiation. The more intense the radiation, the fewer disk-bearing stars that you have. In terms of What this means, though, for the signature of where you see disk-bearing stars in star-forming clusters, I think it's a little bit hard to expect any particular structure of where you have the disk-bearing stars, particularly if you're in a dynamically young region that's not necessarily mass segregated. This is an argument Richard Parker and I made looking at Trumpler 14 and Trumpler 16 in the Carina Nebula, where you're looking sort of at a 2D projection of a 3D structure. And the stars are moving. So you'll have a disk-bearing star that's sort of falling towards the higher FeV intensity region, and you'll have the now evaporated stars moving out from that region, sort of intermixing the disk and the diskless stars in that region. So it's not necessarily clear what kind of structure in the disk population you would expect in these regions. I think one of the other challenges, if you're looking for, say, candidate proplids in high mass star forming regions, so things that are going to be 4 to 5 times more distant than Orion, is trying to figure out what your observational tracer is. So some of those images taken from the ground looking for that H-alpha teardrop shape, when done with higher quality imaging in these types of environments, turn out to actually be much larger evaporating gaseous globules. In a few places in, say, the center of Trumpler 14, where the high quality of HST imaging has revealed some interesting looking H-alpha features, subsequent ALMA observations trying to detect the millimeter dust continuum so far haven't found anything. So I think maybe there is some interesting room for discussion in terms of what sort of observational tracers we might be looking for in these kinds of regions to say, yes, this is definitely the signature of the external impact of the environment on the disks themselves. So for the moment, though, I'm to come back to how the cluster evolution is part of this question of how the environment is affecting star-planet formation. I am heartened to see simulations like this one from Tim Lichtenberg starting to come together that's looking at the dynamical evolution of the region and then tracking how these stars are moving and what that means for the survival of their protoplanetary disks under dynamical interactions in these clustered regions and under external photoevaporation from the high mass stars in the region, all the way up to the point where these disks are potentially enriched with the supernova explosions of those high mass stars. So I'm just about done here. I just want to take one moment to highlight a couple of upcoming observational capabilities that I think will help us continue to move forward and how the cluster dynamical evolution is tied to the outcome of planet formation. And that's just to note that Gaia will continue to improve the quality of the proper motions and kinematic measurements that we're getting for star clusters. Early data release 3 is expected on the 3rd of December, so please stay tuned for that. And so using those kinds of proper motion and sort of kinematic measurements, both to improve our understanding of the membership, what's in these clusters in the first place, and then using that to understand how the clusters are evolving kinematically and ultimately how they will dissolve and join the field. And then there are several upcoming large spectroscopic campaigns that will provide not only radial velocities of these stars, but also provide some age information for different stars and accretion indicators for large enough stars to be able to look at this in sort of a spatially structured way. Again, a nice way to follow up evidence for, say, 3 different age populations in the ONC. And finally, I'll just note some incredible infrared instruments to be looking forward to into the future, allowing us to probe both more embedded regions, younger regions, and perhaps also think about how else we're looking for evidence of the impact of environment on the disks. So with that, I will just put up my final slide, and I'm happy to take any questions.